All right, Calc kids, this is section 7.4. Now we are going to be solving exponential and log equations. And I kind of mentioned in the last section that exponential and log functions are inverses of each other, okay? Which is basically like they undo one another. So if you ever have an equation that has an exponential function and you're trying to solve it and get rid of the exponential part of it, you could take the log of that function, or vice versa, if you have a log function and you're trying to get rid of a log, you can take and change it to an exponential function, and it will kind of help solve itself, and you'll kind of see that down below here. So there's some properties that they talk about here, and basically they say like this is a one-to-one property. So this is an exponential one-to-one property, and this is a log one-to-one property, and then they have inverse properties. So let's look at these exponential ones. So an example for this one-to-one property here would be like 3 squared equals 3 to the x power, okay? And they're basically saying solve for x. Well, x has to be 2 in that case, right? X equals 2. Because the bases are the same, the exponents have to be equal to each other. So that's a one-to-one property. Same thing here. So like if you have log base 3 of 2 equals log base 3 of x, well, the log base 3's are going to be the same. So kind of, if it helps you to think about it as like canceling them out, that will work, but this x has to be a 2 in order for those two things to be equal to each other. So those are one-to-one properties. But then you also have inverse properties. So this starts with an exponential function and then it has the log in the exponent. And those two things will cancel with each other as long as the bases are the same number. And x will be equal to x. So an example of that would be like 3 log base 3 of 7 would be equal to 7, because these two parts would cancel out and 7 would be all that you have left. Okay. Same thing if we have log base 3 of 3 to the 7th power. That would be equal to 7 because those two are going to cancel with each other. So this starts with a log first and then has an exponential function. So starting with an exponent, then you have a log. Starting with a log, then you have an exponent. Those two things will cancel out with each other. And then you'll just have the part that's left over. Okay, so they want us to solve some things or rewrite the equation here. So we'll do a few of these. A, they have 2 to the x power equals 32. Okay. And there's many different ways that you can solve this. This is just one way. So what I like to do is I like to change the base here. 32, if I can change that to like 2 to some power, right? 32 would be 2 to the 5th power, okay? So I have 2 to the x power equals 2 to the 5th power. So I know that x has to be, in that case, 5. And the property that I used was this one-to-one exponential property, like this 3 example right here. So this is, I'm going to do 1-1. Okay, that's my symbol for property, 1-1. Okay, this one says ln of x minus ln 3, okay, equals 0. So let's do this. What I'm going to do is I'm going to move this ln to the other side. Okay, and so when I do that, I would have ln of x equals ln of 3. And in that case, the ln's kind of cancel out with each other, so I just have x is equal to 3, which is another one-to-one property, but it's the log one-to-one property. Okay, because if the logs are the same on both sides, then you can just cancel them out. Okay, so I have that. C, if I do this one, what I can do here is I can do that change of base again. This one's a little bit more confusing. 1/3 can be written as 3 to the negative 1 power, right? That's what 1/3 is, 3 to the negative 1 power. And then I'll leave that x there. Okay, the 9 can be rewritten as 3 to the 2nd power. Okay, so I change this 1/3 and I change the 9. Instead of just changing the 32 and leaving the 2 like I did here, I'm changing both of them to a base of 3. Okay, so this would really be like 3 to the negative x power if I combine the negative 1 and the x. So I have 3 to the negative x power equals 3 to the 2 power. So I have Negative x in that case would be equal to 2, and x would be equal to negative 2 in that case, okay? And that's another one-to-one property, okay, that I just did. So I converted those bases, and then I solved. All right, now, these ones have an exponent, so this first one, d, has an exponential function, and I'm trying to get rid of it, okay? So what this will look like, I have e to the x power equals 7, and I'm trying to get rid of it. So what I can do is I can basically do the inverse operations of the inverse property. When I have this exponential function, the opposite of e would be like log with base of e, and those two would cancel each other out, right? Log base e, but if I do that log base e to the one side, I have to do the log base e to the other side. So this would be log base e of x equals log base e 7, right? And then the log base e's can cancel out with each other, so I would just have x would be equal to log base e of 7, okay? But remember that log base e is also the same thing as ln, so x would be equal to ln of 7, okay? And that was using an inverse property. I basically inserted a log in there when there wasn't one to try to get that exponential function to go away, okay? So if you don't want to write it as log base e to start with, you can just use ln, and that's fine. So ln will cancel the e out, okay? Now here I have a log, and I want to get rid of it. So I would have, I'm going to raise it to a power of e. So what this will look like is e to the power of ln x equals e to the negative third power, okay? And so this e and this ln will cancel out, so I will have x equals e to the negative third power, or if I want to change that to be a positive power, it would be 1 over e to the positive third power. And that would be my solution there. And again, I used an inverse function, okay? Last one, I have log base 10 of x, and I want to try to get rid of that log base 10, so I'm going to raise it to a power of 10, because that's the base, okay? That's what the opposite of log base 10 would be 10 to some power. Okay, the opposite of ln would be e, the opposite of 10 would be 10, opposite of log base 10 would be 10 to some power. So this guy will cancel out there, and I will have x equals 10 to the negative first power, or x equals 1 over 10 to the positive first power. Is that what that will look like? And again, that was an inverse function. Okay, so these last three are a little bit harder to understand because I'm inserting things when they're not already there. These ones I'm just changing just a little bit. So here are some strategies for solving exponential functions. What I want to first do is I want to try one of these strategies, A, B, or C. I want to try to rewrite it in any way that I can so that I can simplify things. And if then I can't, I'm going to take and rewrite that exponential function in terms of log, or insert a log or an exponential function. So I'm going to do one of those two. If it's an exponential function, I'm going to change it to a log, or insert a log. If there's a log function, I'm going to insert an exponential function, okay, to get that to go away and solve, right? So let's do a couple of these. Number one, I'm trying to solve for x, okay? So what people try to do here is the 3 and the 2, they try to multiply those together, but that doesn't work. What I would do first is I would divide the 3 over. So I would have 2 to the x power equals 42 divided by 3 is 14, okay? And then, is that 14? No, that is not right. 42 divided by 3. 14. Yes. That's right. So 2 to the x power equals 14. Okay. Now, it would be really nice if I could change this 14 to be, a power of 2 or something, but 2 to some power will never give me 14. Like 2 to the third power is 8, 2 to the fourth power is 16. That doesn't work. So what I can do is I can put a log in front of both sides, or ln is what a lot of times people do. So I will do ln of 2 to the x power and ln of 14, okay? And then I can bring that x down in front, okay? So x ln of 2 equals ln 14. So I'm inserting a log when there wasn't already one there. And then what I can do is to get the x by itself, I would divide by ln of 2. Divide by ln of 2. Okay, so x would be equal to ln 14 divided by ln of 2. And don't just do ln of 14 divided by 2. You have to do ln's for both of them. So ln of 14 divided by ln of 2. And that gives me 3.81, just about. Okay, 3.807, 3.81. Okay. Now you might be wondering, why did I insert an ln rather than a log base 2 or a log base 10 or something like that? As long as I do the same thing to both sides, it doesn't really matter. I could have inserted a log base 10 to both sides, it doesn't matter. But I just like to use ln just because it's less writing than log with base of something really clunky. Okay. So next one, number 2. I have an e to some power, and anytime you see e, you always want to use ln. Okay, so I have ln. I'm going to use that to get him to go away. So basically, I have x plus 1 equals ln of 4. Okay, and then what I can do is I can subtract the 1. Okay, but that doesn't make it ln of 3. That just makes it ln of 4, and then I would subtract 1. That's what x will be equal to. So then I just type that in. ln of 4, close parentheses. I don't know if you can see my calculator here very well. Yep, there you go. Minus 1. Okay. And I get 0.39. Actually, let's go 3 decimal places. 0.386 is what he will be. Okay. All right, so a couple more of these. This one, number 3. I'm going to get rid of everything else that I can ahead of time. So I'm going to add the 4 to here, which will make that 15. And so, oh boy, let's write this out. 2t minus 5 equals 15. Okay, then I'm going to divide by 2 to get that to go away. So even though I'll end up with a decimal over there, whatever. 3 to the 2t minus 5 equals 7.5. Okay. Now, I can't get 3 and 7.5 to be the same base, like the 2 and the 32 on the front side. So I ln both sides, or you can do log base 10 of both sides, or whatever you would like to do. And by doing that, that allows me to bring this guy down in front. Okay, so I have 2t minus 5 times ln of 3 equals ln of 7.5. Okay, so that's what it will look like now. All right, now, if I'm trying to solve for t, I'm going to divide the ln of 3 over to the other side. Okay, so I have 2t minus 5 equals ln of 7.5 divided by ln of 3. I'm going to go ahead and type that in. Okay, ln 7.5, close parentheses, divided by ln of 3. And I get 1.834. Okay. Then I need to solve for t, so I'm going to add the 5 and then divide by 2. So plus 5 divided by 2, and I get t is going to be 3.417 is what my t is. Okay. All right. Number 4 is probably the easiest one in the whole sheet, just because there's a log 3 on both sides. So since there's a log 3, I can just cancel those 2 out on both sides and then just solve for x from there. So I'm going to subtract x here, and I'm going to add the 1. So 4x will be equal to 8, and x equals 2. That one was kind of nice. Okay. Number 5. First thing I would do is divide by 2, because there's a 2 out in front. Okay. So I have log base 5 of 3x equals 2. Okay. And then I have a log base 5 and I want to get rid of it. Okay. So the easiest thing to do there is, since it's a base of 5, right? All these other ones had like log base e or log or ln's or whatever. I'm going to raise it to a power of 5 for this one, because that's going to make that go away. Okay. So I will have 3x equals 5 to the second power. Okay. So when these two cancel, that 3x will come down, and that will still stay 5 to the second power on the right side. Okay, so 5 to the second power is 25. So I have 3x equals 25, and if I divide by 3, x is going to be 25 over 3. Let's just leave it like that. We won't convert it to a decimal. But if you have a base that's other than e or something really nice, go ahead and raise it to that exponential function of that. Okay, so in a lot of these we used inverse properties because we inserted a log when we were trying to get rid of an exponential function, that type of thing. Okay, and that's what we're going to do down here for these next two examples. So this is a PERT equation because we're using compounded continuously. You've deposited $500 into an account. Okay, so 500 is going to be your P, because that's the principal, that's the amount that you're putting in. 6.75, that's your interest rate. And how long will it take to double? Okay, I circle or box or something the words how long, because that tells me what I'm solving for. How long will it take for your stuff to double? How long means I'm solving for T, okay? And to double means that my after amount will be double what I started with. Well, if I'm starting with 5,000, then that means my after amount has to be, I'm starting with 500, my after amount has to be 1,000. Okay, so you kind of have to think about that just for a little bit. So now I just plug stuff in and let's see what we get. I have 1,000 here for A. P is going to be 500. E to the R, and we need to convert that to a decimal first, so 0.0675. And T is what I'm solving for. Okay, so now this is where it is important to know how logs and exponential functions reverse each other. The first thing I'm going to do is I'm going to divide by 500. Okay, so divide by 500. And what that will do is that will make 2 equals e to the 0.0675 t. Okay, and I'm solving for t, and I'm trying to get that t out of the exponent, but it's like trapped up there. Okay, so I have to basically tackle the ln and tackle the e and get him out of there. Okay, and what gets rid of e is natural log, or ln. Okay, so those two will cancel each other out. So I will have ln of 2 equals 0.0675 t. And if I want to get t by itself, I just divide by that really ugly decimal on both sides, 0.0675. And t will be equal to, I'm going to take natural log, ln of 2, close your parentheses, divided by 0.0675. And that will give me 10.3. And it says how long. Compound interest equations are always set up per year. So it will be 10.3, I'll put years in there instead of just y. So 10.3 years is how long it will take. Okay, last one. The average salaries for secondary teachers from 1980 to 2002 can be modeled by this equation. And let's see, these are in thousands of dollars. So this would be like 42,000, this would be 24,000, etc. T equals 10 represents 1980. So they're starting year 0. Year 0 would correspond to 1970. 10 is 1980, etc. And we would go all the way through there. Okay. Let's see. During which year did the average salary for secondary teachers reach 2.5 times its 1980 level, which was 16.5 thousand? Okay. So they worded that really weird. When did it reach 2.5 times this amount? Okay, so let's just take 2.5 times that amount, and let's see what we get. 2.5 times 16.5. They want to know when it reached 41.25 thousand. Okay, they want to know when, during which year. That's what we're solving for, which means we're solving for t. So then I have to have something to plug in for y, and that's going to be the 41.25 that we just found. Okay, so 41.25 equals negative 42.3 plus 24.9 ln of t. Oh man. Okay. All right, now we've got to do some rearranging here and get rid of anything that we can. So I'm going to add the 42.3 over, and that will be gone there. So this will be 83.55, I think, if I did that in my head right. Okay, check 83.55, yes, okay. Now let's divide the 24.9 over so that we just have ln of t by itself. I can't do that in my head. So 83.55 divided by 24.9. and I get 3.355 equals ln of t. Okay, scroll down. Now I have an ln, and the t is trapped inside of the ln, and I want to get rid of the ln. So what I'm going to do is I'm going to raise each one to a power of e. Okay, so this is like e to the power of 3.355, e to the power of ln, which makes that just go away, and the t will just kind of fall down. So t is going to be equal to e to that power. So I'm going to do e to that answer, and t will give me 28.66 years. And then one more thing that we need to do, we need to figure out what year that is, because we need to know what year, not how many years later. Okay, so if year 0 is 1970, 28 years past that, or almost 29 years. Let's see, 28 plus 1970. It will be year 1998, maybe like September of 1998, or maybe August of 1998, something like that. Partway through the year of 1988 is when that will occur. Okay, so that was a lot of material to go through, a lot of example problems. Some of them are really short, but really this is the last two examples that we did was really why logs and exponential functions are really important. Okay.